In this final lecture of this module, we'll cover a final example of a colligative property that's called osmotic pressure. Osmotic pressure is in some ways a rather strange property of solutions. So as we cover this, try to keep the following in mind. It involves the passage of water molecules through what we're going to call a semi-permeable membrane that blocks the passage of any solute molecules or ions. In other words, we're going to be working with some sort of barrier, we'll call it a membrane, that's semi-permeable, meaning it's only permeable, or it only allows water molecules, in this case because water will be our solvent molecules to pass through, but not any solute particles. And it's best represented, this concept of osmotic pressure, with a series of cartoons or figures. So below is the first of two figures. Suppose we have a U-tube, and you can see why this tube here, which is open at either end, would be called a U-tube, is filled with pure solvent. In this case, the solvent is water, on the right side of a semi-permeable membrane. So here we have our semi-permeable membrane or barrier. We're going to fill the right-hand side with just water molecules, and the individual water molecules are shown here. And then we're going to put an equal volume of an aqueous solution of some solute dissolved in water on the left side of the semi-permeable membrane. Notice then that we have a solution on the left, solvent on the right, and that these two levels are equal. So the solution and the pure solvent meet on either side of this semi-permeable membrane. If you have a situation like this set up, it turns out there's a natural driving force to try and make the concentration of solute the same on both sides of that membrane. If you recall, the membrane is semi-permeable, so it only allows the passage of water molecules. Only water molecules can pass. So the only way the system can attempt to equalize the solute concentration on both sides of this membrane is to attempt to dilute the solution on the left here by a net flow of water molecules from right to left. Again, there's a driving force to try to get these two solutions, these two sides of the membrane, at equal concentration of solute. On the right-hand side, in our example here, we just have solvent, and there's no solute. On the left-hand side, there's solute. If we want to get these two concentrations of solute equal, 0 on the right and whatever this number is on the left, the only way we can even attempt to do that would be to have water molecules flow in the net sense from right to left and try to dilute this solution down closer to a concentration of 0, which is what the concentration is on the right. So you notice in the diagram, there's two arrows to the left showing the flow of water molecules for every arrow moving to the right. So water can move back and forth, but there's a net flow of water from right to left, and the driving force for this is to try to get these two solutions. I keep calling this side a solution, and it's not, the right-hand side, to get these two sides the same concentration of solute. What we have here is osmosis occurring. It's the net movement of solvent from the side with the lower, or in this case, 0 concentration of solute, to the side with the higher concentration of solute. So we have a net flow of water from the right to the left. Now, even though the concentration of solute will never be the same on both sides, and the reason in this case is because we can never get the concentration of solute here to 0, which is what it is on the right. But it doesn't keep the system from trying. So what I've written here is the system is hell-bent on diluting that left side as much as possible by the net flow of water from the right-hand side going to the left. Now, won't this cause the liquid level on the left here to go up and that on the right to go down? And yes, it will. So let's look at our second figure. The first thing you'll notice here is we have our same U-tube, and lo and behold, if we let a period of time pass, the level of solvent on the right is lower. The level of now diluted solution on the left is higher because water has flowed from the right to the left in the net sense. Now the rising column of diluted solution on the left starts to exert a back pressure, and that back pressure is shown with this green down arrow. So there's this driving force for water in the net sense to go from right to left, but as it does that, there's increasing pressure on the left, meaning this column's getting higher, so the pressure of that column of solution is pushing back down. And what's going to happen is that there's going to come a point at which that back pressure from this diluted solution is high enough that it's going to stop the net flow of water from the right to the left. And at that point, the level of solution on the left stops going up. The level of solution on the right stops going down. This back pressure from the diluted solution column is what's caused the stopping of the net flow of water. And so now we have arrows, equal arrows going to the right and to the left of water going across this membrane. We've reached an equilibrium situation. Now the downward hydrostatic pressure of the column of the excess diluted solution on the left is the pressure needed to stop the net flow of water from right to left. And it turns out that this hydrostatic pressure is a characteristic now of this diluted solution. It's called the osmotic pressure of that solution. Osmotic pressure is often symbolized by a capital Greek pi. And if we started with an even more concentrated solution on the right, the resulting column if we started with an even more concentrated solution on the left here, when the system reached equilibrium, even more water would have flowed in the net sense from the right to the left. So if this solution started out more concentrated, this column would have gotten higher before the back pressure stopped the net flow of water. So what I'm trying to tell you is the more concentrated the solution, the higher the osmotic pressure. If we write an equation for osmotic pressure, we can see that there's a direct relationship between the osmotic pressure and capital M here, which is the molarity, the concentration of the solution. So let's define all the parameters in our equation for osmotic pressure. Capital pi is, of course, the osmotic pressure, and in this equation it's in units of atmospheres. I is our friend, the Van't Hoff factor for the solute. Capital M here is the molar concentration of the solute in moles per liter. And please note that for this colligative property, osmotic pressure, we're using molarity, not molality, as we used for freezing point depression and boiling point elevation. R is the gas constant in units of liters atmospheres per degree Kelvin mole, and T is the Kelvin temperature. So let's take this equation and attempt a simple calculation of osmotic pressure. Suppose you were asked to calculate the osmotic pressure in both atmospheres and torr. Our equation will give us the osmotic pressure in atmospheres, and you can convert it to torr. of a 0.0100 molar solution of potassium sulfate at 25 degrees C. Well, this would appear to be straightforward. You simply calculate the osmotic pressure using the gas constant and the information given. So here's our equation. And the first thing we need to do is decide what value we'll use for the Van Hoff constant. And absent experimental data, we can say that 3 would be a reasonable first guess. And the reason would be, of course, that if you take potassium sulfate, you dissolve it in water, you get 3 particles per formula unit of potassium sulfate, 2 potassium ions and 1 sulfate ion. Our temperature would be 298 K. So if we put all of our parameters in our equation for osmotic pressure, we'd have 3 times 0.1 moles per liter, that was the given molarity, times the gas constant, times the temperature, and of course, liters and moles and Kelvin temperature would all cancel out, leaving atmospheres, and we'd be left with an osmotic pressure of 0.734 atmospheres for this 0.0100 molar solution of potassium sulfate at 25 degrees C. We can convert to torr by simply remembering that an atmosphere is 760 torr, and so our osmotic pressure in torr would be 558. Now, some things to note here. The first is the osmotic pressure seems rather large. This is about 3/4 of normal atmospheric pressure, especially for a solution that seems pretty dilute. What that means is that osmotic pressure measurements might be a very sensitive experimental method for determining solution concentrations. We'll talk a little bit more on this in a few minutes. The other thing I want to mention here is the Van Hoff factor for this equation is probably less than 3, considering the fact that potassium sulfate contains sulfate -2, which is a higher charged anion than, of course, -1 or +1. Now, on a previous lecture, there was a table of Van Hoff factors for potassium sulfate solutions, only instead of for 0.0100 molar, it was listed for 0.0100 molal. That number was listed as 2.7 for I. If we keep in mind that for fairly dilute solutions, which is what these are, the molarity and molality numbers tend to get fairly close to each other. So without any other information available, we can probably say that I equals 2.7 is probably a better value to use than 3 in this equation. If we did that, it would reduce our calculated value of the osmotic pressure down to 0.661 atmospheres, or around 500 torr. Now recall that a previous lecture covered vapor pressure lowerings, freezing point depressions, and boiling point elevations for glucose and sodium chloride solutions. So what I'm going to try to do here is calculate the osmotic pressures for a 0.01 molar solution of glucose, so we can compare it to our 0.01 molar solution of potassium sulfate, and also for 0.01 molar sodium chloride, again, to compare with our 0.01 molar potassium sulfate. So let's go ahead and do that. Well, let's look at the glucose calculation, calculating the osmotic pressure for a 0.01 molar solution of glucose. If we do that, this should be fairly straightforward, and we're going to use I equals 1 because glucose is a non-electrolyte. We get a osmotic pressure of 0.245 atmospheres, and we'll assume 25 degrees C. Converting this to torr gives us 186 torr. If we do the same calculation for sodium chloride, Instead of I equals 2, I'm going to use a value of 1.87. I think I can defend that in a minute. If I do that, I get 0.457 atmospheres, or 347 torr. Now what about this I equals 1.87? Well, from that previous table in lecture 3, we actually had a value for I for sodium chloride for a 0.0100 molal solution. And again, when we're talking about solutions that are this dilute, a 0.01 molal solution is in fact pretty close to a 0.01 molar solution. In fact, I looked up some densities and did this calculation, and the 0.01 molal solution of sodium chloride's equivalent to a 0.00977 molar solution of sodium chloride. These two numbers are very close. So using this as the Van Hoff factor here seemed pretty reasonable. So I have a table here which summarizes osmotic pressures for the three solutions that we've just talked about, all at the same concentrations, 0.01 molar. And listed the Van Hoff factors here. You can see that osmotic pressure increases with an increase in the number of solute particles. And you say, well, wait a minute, these are all the same concentrations. Why are the osmotic pressures increasing? Well, remember, the number of particles will depend on the Van Hoff factor. So the Van Hoff factor for the non-electrolyte glucose is 1, but sodium chloride produces almost twice as many particles as glucose when it dissolves, so its osmotic pressure is about twice that of the glucose, and the potassium sulfate produces about 3 particles for every one that dissolves. So its osmotic pressure is about 3 times that of glucose. So indeed, osmotic pressure increases with an increase in the number of solute particles, and that's why it's a colligative property. It's important to remember that osmosis will occur across a semi-permeable membrane whenever two aqueous solutions of different concentrations meet at the membrane. In our example, we had pure water on one side and a solution on the other, but you could have solutions of two different concentrations meeting at that semi-permeable membrane. There will be a net movement of water molecules from the solution of lower concentration to the solution of higher concentration. There is some terminology that you should be familiar with associated with the comparison of the osmotic pressures of two aqueous solutions of different or equal concentrations on either side of a semi-permeable membrane. Let's suppose you have solutions of two different concentrations of the same solute meeting at either side of this semi-permeable membrane. So the left-hand side, in this case, is the more dilute solution. The right-hand side is a more concentrated solution. We say the solution that has the lower concentration has a lower osmotic pressure. That makes sense. Remember, osmotic pressure is directly proportional to the molarity of the solution, and this side would have the higher osmotic pressure. There'll be a net flow of water to the right until equilibrium is reached. And that would be when the two sides have, hopefully, equal concentrations. You might say, you know, it seems kind of weird or backwards to say that water will flow from the solution with the lower osmotic pressure to the one with the higher osmotic pressure. But remember, the whole point of osmosis is that you have water molecules, solvent, in this case water molecules, where the driving force is for these water molecules to flow in the direction that dilutes the higher concentration of solution. What we'd say in this situation is we'd say that the lower concentration solution is hypotonic compared to the higher concentration on the right, and we'd say this solution on the right is hypertonic, has a higher osmotic pressure compared to the 0.01 molar solution on the left. If you had two solutions of equal concentrations meeting at a semi-permeable membrane, you would automatically have equal flow of water in either direction. The solutions would have equal osmotic pressures. There'd be no net flow of water in either way. Of course, water would flow either way, but the rates of flow to the left and to the right would be equal. What we'd say here is that these solutions are isotonic with each other. They have the same osmotic pressure. The terminology hypotonic, hypertonic, and isotonic will help in describing how red blood cells, which have semi-permeable membranes, exist in the aqueous environment of the bloodstream. I have some cartoons here that will hopefully depict what happens when a red blood cell finds itself in an environment that's isotonic with what's in the red blood cell, hypertonic compared to the solution in the red blood cell, or hypotonic. Here's our picture of a red blood cell, and suppose it finds itself in an isotonic environment. What that means is that the osmotic pressure of the intracellular fluid, the fluid inside, is equal to the osmotic pressure of the extracellular fluid. Basically, this means the concentration of the solutes in the red blood cell are equal to the concentration of the solutes external to the red blood cell. And here we have a healthy red blood cell where water molecules are passing into and out of the cell at equal rates. Red blood cells are happy. Suppose a red blood cell found itself in a hypertonic environment. So what that means is that the extracellular fluid has a higher concentration of solutes, has a higher osmotic pressure than the fluids inside the cell. So we have the osmotic pressure inside of the solutions inside the cell less than the osmotic pressure of the fluids outside the cell. What would happen is, of course, water molecules in the net sense would flow out of the red blood cell, trying to dilute the solution, the external solution. And the red blood cell would eventually be destroyed because it would shrink from the loss of water. And that process is called crenation. If you take a red blood cell and say you just put it in pure water, it's going to be in trouble because pure water, for example, would be a hypotonic environment, very low osmotic pressure. So we'd say that the osmotic pressure of the intracellular fluid is much higher than that of the extracellular fluid. So water molecules would rush in from outside trying to dilute the higher concentration of solute in the cell, and the red blood cell would just swell up and actually explode. The process is called hemolysis. So when you get an IV, the IV solution must be isotonic with your blood so as to not adversely affect your red blood cells. An IV solution that's isotonic with blood will have dissolved electrolytes and possibly some non-electrolytes at the correct concentrations to give the solution the same osmotic pressure as your blood. Now we can do a quick calculation to decide what concentration of, say, sodium chloride would give a solution that's isotonic with blood. So let's do that. It turns out, if you look this up, the average osmotic pressure of blood has been reported to be around 7.7 atmospheres at 25 degrees C. So that is the osmotic pressure we're shooting for in our sodium chloride solution. So calculate the molar concentration of sodium chloride that would be required to obtain an aqueous solution to be used as an IV fluid that would be isotonic with the blood. In other words, have this as an osmotic pressure. So we can use the equation for osmotic pressure to just calculate the molarity of the sodium chloride solution needed. So what I did here was I solved for M, and I put in values for the osmotic pressure because that's our target osmotic pressure. I'm going to put a 2 in for I because it's sodium chloride, and I'll put in the gas constant and the temperature given in Kelvin, and I get a concentration of 0.16 molar. And again, in the absence of experimental data to use immediately here, we'll assume a 2 for the I value of NaCl. What we need to do now is, so this is our answer. This would be the concentration of the sodium chloride that you'd want in that IV bag if you were just giving them water with saline, sodium chloride. Often IV bags have percent masses on them, so why don't we convert 0.16 molar sodium chloride to a mass percent of sodium chloride. And to do that, I'm just going to assume we have a liter of 0.16 molar sodium chloride. And I looked up some data to try to estimate what the density of this solution would be. And my estimate from experimental data, extrapolated from experimental data, is just barely over 1. So what I want to do here is say, okay, with our assumption, 1 liter of 0.16 molar sodium chloride would contain 0.16 moles of sodium chloride. Because molarity is 0.16 moles per liter, so I will calculate the mass of sodium chloride in my assumed 1 liter of solution, and it turns out to be 9.35 grams. I can calculate the mass of the solution from this density, and the mass of the solution, my 1 liter of solution, is just barely over 1,000 grams. And now I can calculate the mass percent of sodium chloride because it would be the mass of the sodium chloride divided by the mass of the solution times 100, and I get around 0.9% sodium chloride by mass. And not coincidentally, a 0.9% sodium chloride solution is often referred to as physiological saline and can be the basis for the solution used for IV bags and or for eye wash solutions or contact lens cleaning. Let's try to use some osmotic pressure measurements to determine the molecular weight or molar mass of a solute. If you recall in the previous lecture, we used, I think, freezing point depression information to calculate the molar mass of a solute. Here we'll use osmotic pressure measurements. So recall from an earlier slide that even very dilute solutions can show measurable osmotic pressures. So we can use this to our advantage, somewhat indirectly, in determining the molecular weight of large molecules that often don't show high solubilities in solvents. So if we can only make a dilute solution, that's okay. We ought to be able to get a measurable osmotic pressure. So suppose a very small but precisely known mass, 1.95 milligrams of a certain protein, which is in this case a non-electrolyte, is dissolved in enough water to make 2 milliliters of solution. So this is a tiny amount of protein in a tiny amount of water to make a tiny amount of solution. The osmotic pressure of the solution, it doesn't say how this is measured. You have to take that on faith. The osmotic pressure of the solution was found to be 1.35 torr at 25 degrees C. So let's use this information to calculate the molar mass of the protein. Well, if you look at the osmotic pressure equation, it doesn't look like it gives us a way to calculate a molar mass directly, but it does give us a way to find the molar concentration of this solution. So let's see if we can do that. If you solve for m here and assign values to the various variables, the osmotic pressure, which is quoted as 1.35 torr, we need to convert back to atmospheres. I would be 1 because we explicitly stated this was a non-electrolyte. We have our good friend the gas constant, and we were told this was done at 25 degrees C. So here it looks like I'm carrying an extra significant figure for a second. So let's calculate M, the molarity. When we do that, we get 7.26 times 10 to the minus 5 moles per liter. That's a pretty dilute solution. What are we going to do with that? Well, we can use the molarity here and the total volume of the solution, which is what we have, to calculate the number of moles of protein present. Because remember, if you want to count, you take the concentration and multiply by the volume of the solution. Concentration times the volume in liters gives 1.45 times 10 to the minus 7 moles of the protein. Now this looks like an even more ridiculously small number. It is. But remember, we now can get the molar mass because molar mass is grams per mole. We know how many grams we weighed out, especially after we convert 1.95 milligrams to grams, and we know how many moles this many grams represents. So we can simply take the mass of the protein in grams, divide by the number of moles of protein, and get units of grams per mole. So this is around 13,400 for a molar mass, which is pretty large. That's okay. Proteins are very large molecules. So what we've done here is we've effectively used the very high sensitivity method of osmotic pressure measurement to gather data that allowed us to get a good number for a molar mass of a very large molecule, in this case a protein. Now here's one more application of osmosis that you might be familiar with. It's called reverse osmosis. And in reverse osmosis, not surprisingly, something goes backwards. What we're doing here is we're applying external pressure, and that pressure is greater than the osmotic pressure of the solution in order to literally squeeze water out of the solution. Remember we said that water molecules tend to want to go from pure water into the solution through the semi-permeable membrane, or from the lower concentration solution to the higher one. Well, what we're going to do is put extra pressure on that higher concentration solution and push the molecules backwards. Reverse osmosis. This, interestingly, can be the basis for home purification of water or even desalination of water. This diagram ought to look familiar here. What we have is this situation where water molecules, because we had pure water on the right and some solution on the left, have in the net sense flowed from right to left and made this solution here column higher. And then what happens is the net flow of water stops eventually from the osmotic pressure of this solution pushing down or pushing back. Well, this solution here we could pretend is either seawater, municipal water. I should say municipal water, that would be water you would drink, or seawater containing lots of dissolved solutes. And what we're going to do is not just rely on the osmotic pressure of the solution, but we're literally going to add extra external pressure and push down on this solution. Well, what's going to happen? Well, notice that these arrows now that we're adding this external pressure that represent the net flow of water are all going to the right because we're adding this external pressure above and beyond the osmotic pressure. we're literally squeezing water molecules out from the solution on the left and into the pure water side on the right. So as we add pressure, the level of this solution is going to go down and the pure water level will go up. We're squeezing water out of this dirty solution. So this level of water will rise as we add this external pressure. Now the next slide has a link to a video demonstrating the desalination of seawater using reverse osmosis. Now I don't know whether you'll get this video to work or not. You can try it, but I do have a frame from the video here, and we'll just spend a couple seconds looking at this. What we have is a semi-permeable membrane with pure water on the left and seawater on the right, and we apply a high pressure to the side containing the dissolved salts, the seawater, and what we're doing here is we're forcing water molecules back through the membrane in the direction they wouldn't ordinarily want to travel. Remember, in the absence of this external pressure that we're applying by osmosis, water molecules would naturally want to flow in the net sense from left to right in order to dilute the solution. But what we're doing here is we're forcing water molecules in the net overall sense. And I keep saying that because water's always going back and forth across this membrane. But in the net sense, if we put pressure on the right-hand side, more water molecules are being moved from right to left than in the reverse direction. So we're literally using external pressure to squeeze pure water out of the seawater and into the left-hand side. This is a very good example of using the principles of osmosis in a very practical way.